Greetings, class! So, have you ever wondered why a heavy box, once you stop pushing it, just eventually grinds to a halt? Or, on the completely flip side of things, how a massive rocket manages to accelerate in the complete empty vacuum of space? I mean, there is absolutely nothing around it to push against, right?
Well, these seemingly completely different phenomena are actually governed by the exact same fundamental rules of the universe. Today, we will study force, momentum, and Newton's laws of motion.
Okay, to master this material, our agenda for today's explainer covers 6 key areas. We will start with force and its effects, then friction and constant motion, move on to Newton's first law on inertia, Newton's second law covering F equals ma, Newton's third law on interactions, and finally wrap up with a high-yield summary.
Let's dive right in with Section 1, Force and its Effects, Understanding Pushes, Pulls, and Dimensional Changes.
So, force is this everyday concept that we mostly experience as pushes and pulls. Think about, say, the exertion of force when you're shoving a heavy shopping trolley down an aisle, or gravity just relentlessly pulling a textbook to the floor when it slips off your desk. But here's the thing, forces aren't just about dramatic, visible movement. Take structural integrity. When you casually lean against a solid brick wall, it feels entirely static. Nothing seems to be happening. But on a physical level, the molecular structure of that wall is actively compressing. The electron clouds of the atoms in the wall are literally repelling the electron clouds in your body. It's providing this rigid, continuous counterforce against you to maintain a state of perfect equilibrium. It is a highly complex, dynamic process happening right under your nose, basically keeping you from just falling straight through solid matter. And beyond just maintaining equilibrium, forces also have the incredible power to change an object's physical dimensions or shape entirely. You're applying a mechanical force when you stretch a rubber band, which stores elastic potential energy, or when you completely crush an empty drinks can under your foot. In physics, we really rely on the fact that these physical changes happen in mathematically reproducible ways. Because a specific material deforms in a really predictable manner under a specific load, we can establish strict measurement standards. For example, applying a known amount of force will consistently stretch a calibrated metal spring by the exact same length every single time. That reliable linear relationship, that is exactly how we calibrate a Newton balance to precisely measure applied force in a lab setting. Now, it is absolutely critical to remember that forces are vector quantities. This means they possess both magnitude, which tells us just how strong the push or pull actually is, and direction, which tells us exactly where that force is being applied. In our technical diagrams, we represent these vectors with arrows, and the length of the arrow is directly proportional to the magnitude. But in the real world, objects rarely experience just one force at a time, do they? Imagine 2 people pulling on a heavy rope in exactly the same direction, while their individual forces add together. If they pull in opposite directions, the forces subtract. So the total combined effect of all these independent vector forces acting on a single object, that is what we formally call the resultant force.
These are the key points related to this topic. Focus on them carefully as they are considered essential for your exams.
Moving right along to Section 2, Friction and Constant Motion, Overcoming Historical Misconceptions. Historically, we're talking way back to the days of Aristotle here, scientists genuinely believed you needed a constant, active pushing force just to keep an object moving at a steady pace. They looked at the world and deduced, hey, when you stop pushing a cart, it stops. Makes sense, right? Well, what they hadn't quite realized was that an invisible, ever-present force called friction was actually the culprit slowing things down. If you've got an experimental scenario with a heavy wooden box sliding across a rough concrete floor, the physical force you exert to keep it moving is largely dedicated to fighting the kinetic friction between the box and the floor. To logically optimize this process and reduce that physical resistance, engineers follow a standard step-by-step technical procedure. Step 1, you smooth and polish the contact surfaces to remove all those microscopic, jagged edges. Step 2, you apply a lubricant, like grease or oil. This creates a thin fluid layer between those solid surfaces, drastically dropping the frictional coefficient.
And this brilliantly illustrates our next core concept. Consider what happens if we take this idea to its absolute logical extreme. If we could execute a theoretically perfect scenario where friction is reduced to absolute zero, maybe out in the deep vacuum of interstellar space, super far away from any gravitational bodies, an object in motion would just simply continue moving at a constant speed in a perfectly straight line forever. without any pushing force required at all, no active push needed. Which takes us perfectly into Section 3, Newton's first law, inertia and the resistance to change. Newton's first law of motion formalizes this exact behavior we were just talking about. It dictates that every object continues in its state of rest or continues moving with uniform velocity unless it is acted upon by an external resultant force. And at the very heart of this law is the fundamental concept of inertia. Inertia is defined as the inherent property of an object to resist any changes to its current state of motion. Essentially, matter is exceptionally stubborn. If an object is sitting perfectly still, it deeply wants to stay still. If it's already moving at 40 miles per hour, it strongly prefers to keep moving at exactly 40 miles per hour. It requires a genuine, measurable resultant force to break that stubbornness. We actually see a highly consequential, life-saving contemporary application of this principle in automotive safety design. Imagine you're in a car, traveling at highway speeds. You and the car share the exact same velocity. When the car brakes suddenly, the car's resultant force changes dramatically due to the immense friction applied by the brake pads. However, the passengers inside possess inertia. Your independent physical bodies stubbornly tend to remain in motion at that original highway speed. Without some kind of intervention, a passenger would just continue moving forward right through the windshield. That is exactly why passengers require seatbelts. The tightly woven fabric provides a critical, opposing resultant force that safely and controllably decelerates your body along with the steel frame of the vehicle.
Here are the core details regarding this topic. Review them intently for they are deemed crucial for your finals.
Let's see how this builds into Section 4, Newton's second law, F equals ma, focusing on acceleration and mass. While the first law tells us what happens when there's absolutely no resultant force, the second law describes the exact mathematical reality of what happens when a resultant force is actually applied to an object. Now, to conduct any rigorous, data-driven investigation at the A-level standard, we absolutely must use precise terminology and standard SI units. Force is measured in newtons, designated by the capital symbol N, mass is measured in kilograms, designated by kilograms, and acceleration, which is the rate of change of velocity, is measured in meters per second squared. Using these standardized units is absolutely critical to ensuring our calculations remain universally consistent. For an object possessing a constant mass, these three vital physical quantities are united by one of the most famous and powerful formulas in classical mechanics. F equals ma. Force equals mass times acceleration. This elegant little equation tells us that the acceleration experienced by an object is directly proportional to the applied resultant force. Basically, push something twice as hard and it's going to accelerate twice as fast. Furthermore, because force and acceleration are both vectors, the acceleration always, without exception, occurs in the exact same direction as that applied resultant force. This elegant formula also provides the formal, testable definition for our standard unit of force. A single newton is precisely defined as the exact amount of force required to give a 1 kilogram mass an acceleration of 1 meter per second squared in the direction of that force. From a conceptual standpoint, this really reinforces the idea that mass serves as a direct numerical measure of an object's inertia. The larger the mass, so the more stubborn the object, the greater the force you physically must exert to achieve the very same change in velocity. And now we arrive at Section 5, Newton's third law, interactions, covering equal and opposite forces.
Newton's third law fundamentally shifts our perspective to how multiple objects interact within a system. The law states that whenever one object exerts a force on a second object, the second object exerts an equal and opposite force back on the first. Now listen closely, because here is a very common stumbling block for students that requires absolute clarity. The crucial point regarding the third law is that these two equal and opposite forces always act on completely different objects. They do not act on the same object, which means they do not simply cancel each other out to create zero resultant force. One force acts on object A and the paired force acts on object B. Let's ground this critical concept by analyzing a few real-world scenarios. When you push a heavy supermarket trolley forward, you are exerting a force onto the trolley's handle. Simultaneously, the trolley exerts an equal and mathematically opposite force backward onto your hands, which you can physically feel as resistance. Consider human locomotion. As you walk across a room, your foot actively pushes backwards against the floor. Because of the third law, the floor exerts an equal and opposite friction force forward onto your foot. That forward force from the floor is what actually physically propels your body across the room. And thinking back to the awe-inspiring mystery of our initial hook regarding aerospace dynamics, a rocket does not need air to push against. The rocket engine violently ignites and exerts a massive downward force to expel high-pressure exhaust gases out of its nozzle. Consequently, those expelled gases exert an equal and mathematically opposite upward force on the interior of the rocket engine. That incredible upward thrust is exactly what successfully accelerates a multi-ton spacecraft through the cold, empty vacuum of space. We have covered a tremendous amount of academic ground today. Let's move to Section 6, our high-yield summary, to lock in these core takeaways. Here are your core, undeniable takeaways for your upcoming exams. First, forces are vector quantities that have the power to change an object's state of motion, equilibrium, or physical dimensions. Second, friction is the ever-present physical resistance that causes unwanted deceleration in moving bodies. Third, Newton's first law teaches us about inertia, matter's inherent, stubborn resistance to any change in velocity. Fourth, Newton's second law provides us with F equals ma, defining mathematically how resultant force directly dictates acceleration. And fifth, Newton's third law proves that interaction forces always exist in perfectly equal and opposite pairs that act on distinctly different objects. To finish up our masterclass, I want to leave you with a bit of a thought-provoking physics paradox. If Newton's third law is an unbreakable rule of the universe, and every single exerted force instantly creates a perfectly equal and opposite force, how does anything ever manage to overcome that balance and start moving in the first place? Think deeply about which specific objects those paired forces are actually acting upon, and how resultant force is calculated for a single mass. Have a fantastic day, and never stop questioning the physics of the world around you.
The screen highlights important terms for this topic, arranged based on various exam boards. These keywords require strong focus during preparation due to their importance and must not be overlooked at all. Additionally, there is a past paper review for each board and paper category. Pay attention to this as well, it will greatly enhance your preparation. Moreover, try to understand how each keyword works in context instead of just memorizing it alone. Practicing these terms regularly in past questions will improve your accuracy and exams outcomes.
Please subscribe our channel to get more educational videos. Thank you.